Welcome to Statistics, where we bring complexity to clarity. I am excited to have you join me for our 10th unit, Probability. Probability. What is probability? Let's understand it with the help of an example. There are a number of events in day-to-day life about which one is not sure whether it will occur or not. But one is always curious to know what chances there for a happening or event to occur. For instance, one may be interested to estimate whether it will rain today or not. Or what is the chance that there are 4 aces in one hand in a game of cards among 4 players, etc. The numerical evaluation of chance factor of an event is known as probability. Jacob Bernoulli, an Italian mathematician, was the first to give concept and definition of probability in 1713. Let's begin with understanding experiment. Experiment can be definite or uncertain. The example of definite experiment is, for example, in physics, volume is inversely proportional to pressure is definite. The example for uncertain experiment is tossing a coin. The probability is associated with uncertainties. Hence, the uncertain experiment will take us to the journey of probability. Let's check out the terminologies linked with probability. Beginning with experiment. A happening with 2 or more outcomes is called an experiment. Random experiment. If the outcomes are associated with uncertainties, the experiment is called random experiment. Trial. An experiment which is repeated under essentially identical conditions is known as trial. Event. An event is a collection of possible outcomes which are favorable to a happening out of total outcomes and is denoted by capital E, A, B, C, etc. Sample space. The totality of all possible outcomes of an experiment is called sample space. It is denoted by omega. Let's see an example of random experiment. Here, rolling a die is trial. And all the possible outcomes, that is 1, 2, 3, 4, 5 and 6 is the sample space. A is the event of getting an even number, that is 2, 4 or 6. Now let's see what do we mean by complementary event. An event A bar is said to be complementary to an event A in omega if A bar consists of all those points which are not in A. Example, on rolling a die, if event A is getting an even number, then its complementary event A bar will be getting an odd number. Simple or elementary event. An event having only one sample point is called simple or elementary event. For example, in the experiment of tossing 3 coins at a time, the event A that all the coins turn up with heads consists of only one point, HHH, hence A is a simple event. Equal events. 2 events A and B are said to be equal if A is a subset of B and B is a subset of A. This statement implies that all the points of A are also the points of B, which is indicated by A is a subset of B and vice versa. Compound event. The joint occurrence of 2 or more events in connection with each other is called compound event. Or simply, we can say that an event which is not simple is called a compound event. Equally likely events. Events are said to be equally likely when one does not occur more often than the others. Example, throwing a die, all 6 faces are equally likely to occur. mutually exclusive or disjoint events. Events are said to be mutually exclusive if the occurrence of one precludes the occurrence of the other, or two events A and B are said to be mutually exclusive if there is no point in common between the points belonging to A and B. Example, on rolling a die, if event A is getting an even number and event B is getting an odd number, then events A and B are mutually exclusive events. Exhaustive events. A set of disjoint events A1, A2 up till An is said to be exhaustive if the union of ai's, where I is equal to 1 to up till n is the sample space, that is, union of I is equal to 1 up to n ai is equal to omega. For example, in throwing a die, the spots 1, 2, 3, 4, 5 and 6 are exhaustive events. Impossible event. An event which is certain not to occur is called an impossible event. It is denoted by an empty set phi. Example, the event A, that in 2 throws of a die, the sum of the spots is 1. Here, the event A is an impossible event as in 2 throws of a die, the sum of spots has to be at least 2. Unison of events. Unison of two events A and B means the event which relates to the occurrence of A or B or both. It is denoted by A union B. Example, in rolling of a die, let event A be getting an even number and event B be getting a number less than 3. Then unison of event A or B will be getting 1, 2, 4 or 6. Intersection of events. Intersection of events A and B leads to an event which conforms to the occurrence of A as well as B. Hence, it consists of those points which are common to A and B. It is denoted by A intersection B. Example, in rolling of a die, let event A be getting an even number and event B be getting a number less than 3, then intersection of event A and B will be getting 2. Here we have taken the same example, that is event A is getting an even number while rolling a die, that is getting 2, 4 or 6, and event B is getting a number less than 3, that is 1 or 2. So the union of event A and B will be occurrence of A or B or both, that is all the points 1, 2, 4 and 6, and the intersection of event A and B will be the common occurrence, that is 2. Dependent events. Events where the outcome of one event affects the probability of the other. For example, drawing cards without replacement. Here, event of getting a desired card is dependent of the previous pick, that is, probability of picking a desired card changes in every pick. Hence, it is an example of dependent event. Independent events. Events where the outcome of one event does not affect the probability of the other. Example, tossing a coin and rolling a die. In tossing an unbiased coin, event of getting head in the first toss is independent of getting a head in second, third and subsequent throws. Hence, it is an example of independent event. Now, let's see the concept of classical or Laplacian or mathematical probability. Probability is a ratio of number of favorable cases small n to the total number of equally likely cases capital N. It is denoted by P of A. Symbolically, it can be written as P of A is equal to number of favorable cases divided by total number of equally likely cases, which is equal to small n upon capital N, where 0 less than equal to small n less than equal to capital N. This is also known as a priori probability. Suppose a coin is tossed, the possible outcomes are head and tail. These are equally likely and mutually exclusive events. The probability P of event head is 1 by 2. It can be written as probability of getting head is equal to number of favorable cases, that is getting head, which is 1, divided by total number of equally likely cases, that is head or tail, so it will be 2. Hence, the probability of getting head is 1 by 2. Now, let's see the properties of classical probability of an event A. Probability is a pure number, that is, it has no units. It ranges from 0 to 1, that is 0 less than equal to probability of an event less than equal to 1. And from this we can say that probability can never be negative or greater than unity. It is a relative measure. If A1, A2 up till Ak are k mutually exclusive and exhaustive events in the sample space omega, then summation I is equal to 1 up to k, P of Ai is equal to 1 tends to P of omega is equal to 1. That is, sum of probabilities of all the events is equal to 1. P of phi is equal to 0. That is, probability of an impossible event is 0. If A is a subset of B, then probability of A is less than probability of B. And if B is a subset of A, then probability of A is greater than probability of B. If A plus A bar is equal to omega, then probability of A plus probability of A bar is equal to probability of omega, which is 1, or P of A bar is equal to 1 minus P of A. Let's see it with the help of example of rolling a die. Here omega will be 1, 2, 3, 4, 5 and 6. And let event A be getting an even number, that is 2, 4 or 6. So its complementary event A bar will be getting an odd number, that is 1, 3 or 5. So the probability of A is 3 by 6, which is equal to 1 by 2, and probability of A bar is equal to again 3 by 6, which is equal to 1 by 2. So from the property we have probability of A bar is equal to 1 minus P of A, that is 1 minus 1 by 2, which is equal to 1 by 2. Thus in accordance with the property. Now let's see the demerits of classical probability. Classical probability approach cannot be adopted if any of the following situations exists. That is, if it is not possible to enumerate all possible outcomes, if the outcomes are not independent, if the total number of outcomes is infinite, if each and every outcome is not equally likely. Now let's discuss conditional probability. The possibility of an event or outcome happening based on the existence of a previous event or outcome is called conditional probability. This is written as P of A given B or P of B given A. The formula for it is P of A given B is equal to P of A intersection B divided by P of B, or P of B given A is equal to P of A intersection B divided by P of A. For example, in medical test scenario, it calculates the chance of having a disease when the test result is positive, which can be written as P of A given B, where P of A is the probability of having a disease and P of B is the probability that the test result is positive. Further, if P of A given B is equal to P of A and P of B given A is equal to P of B, then the two events A and B are independent. Let's see it here in the formula. The formula will be P of A intersection B, that is P of A into P of B, divide by P of B, which turns out to be P of A. Thus, P of A given B will be P of A, as the two events are independent. And here, similarly, we will get P of A intersection B will be P of A into P of B, divide by P of A, which gives us P of B. So, P of B given A is equal to P of B. Thus, we can say that the two events A and B are independent. Now, let's see laws of probability. There are three laws. The first is law of complementary event, then law of addition and law of multiplication. Law of addition consists of two cases: when the events are not mutually exclusive and when the events are mutually exclusive. Also, law of multiplication has two cases: when events are independent and events are dependent. Let's discuss them in detail. The first one is law of complementary event A bar. Whenever an event A fails to occur, we may say that event not A has occurred. The event not A is called complement of A and is denoted by A bar. If P is the probability of event A, then probability of its complement A bar is given by P of A bar is equal to 1 minus P of A. This we have already seen with the help of example while discussing the properties. Now let's see it using a Venn diagram. Suppose this is our sample space S and the probability of event A is within this circle. Then the probability of not A will be the entire area outside the circle and within the sample space, that is the shaded region. Further, the second law, that is law of addition, in that the first case is events A and B are not mutually exclusive. If A and B are two arbitrary events in the sample space omega, the probability of the union of A and B is governed by the law P of A union B is equal to P of A plus P of B minus P of A intersection B. Let's see it with the help of Venn diagram. Suppose this is our sample space S and this indicates the probability of event A and this be the probability of event B. Then probability for A union B will be probability of A plus probability of B minus probability of A intersection B, that is we have to subtract the region A intersection B, this region. Hence, the probability of A union B will be the area within this, that is the shaded region. Now, the formula for probability of union of two events can be extended to any number of events. For three arbitrary events A, B and C in omega, the probability of their union is given as probability of A union B union C is equal to probability of A plus B plus C minus probability of A intersection B minus A intersection C minus B intersection C plus probability of A intersection B intersection C. Let's understand with the help of Venn diagram. Suppose this is our sample space S and this is the probability of event A, this be the probability of event B and let this be the probability of event C. Then probability of A union B union C will be probability of A plus probability of B plus probability of C minus probability of A intersection B, A intersection C and B intersection C plus the probability of A intersection B intersection C, that is this area. Hence, the probability of A union B union C is the probability within the shaded region, that is probability within this outline. Further, the second case of law of addition is when events A and B are mutually exclusive. If events A and B are mutually exclusive, then P of A intersection B is equal to 0 and hence P of A union B is equal to P of A plus P of B. This we can get from the previous formula, that is P of A union B is equal to P of A plus P of B minus P of A intersection B. Here, as the two events are mutually exclusive, hence P of A intersection B is equal to 0. Thus, the formula will be P of A plus P of B minus 0, that is equal to P of A plus P of B. So, its Venn diagram will be like, suppose this is our sample space S, and let this be the probability of A and this will be the probability of B. Here the two vents are mutually exclusive, hence they do not intersect. So the probability of A union B will be the shaded region. Now let's see the third law, that is law of multiplication. The first case is event A and B are independent. If two events A and B are independent, the probability of their product is equal to the product of their individual probabilities. Notationally, probability A intersection B is equal to P of A into P of B. Let's see it with the help of Venn diagram. Suppose this is the sample space S and this is the probability of event A and this is the probability of event B. Then the intersection, that is the shaded region, is the probability of A intersection B. This law can be extended to any number of events. For three independent events A, B and C, probability of A, B, C is equal to P of A intersection B intersection C, which is equal to P of A into P of B into P of C. Now we can generate its Venn diagram as follows. Suppose this is our sample space S and we have probability of event A, B and C. Then the probability of A intersection B intersection C is this region. This is probability of A intersection B intersection C. The second case is event A and B are dependent. If two events A and B are dependent, then the probability of both happening at a time is given as P of AB is equal to P of A into P of B given A, or P of B into P of A given B, where P of B given A means the probability of second event B is dependent on the probability of first event A. Here, if P of B given A is equal to P of B and P of A given B is equal to P of A, then the two events A and B are independent, as we have seen in case of conditional probability. Thus, this equation will reduce to P of A intersection B will be P of A into P of B. That is the first case of law of multiplication. This law can be extended to any number of events. For three dependent events A, B and C, P of A intersection B intersection C is equal to P of A into P of B given A into P of C given A and B. Thank you for joining me on this journey through our 10th unit, Probability. If you found this unit helpful, don't forget to like, share and subscribe to Statistics for more insights and clarity on statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.